All right, on to chapter 3. Um, in chapter 1, we talked about collecting data, and in chapter 2, we talked about organizing data. In chapter 3, we're going to talk about describing data. Um, and when describing a set of data, there are 3 important things to consider. First of all, the shape of the distribution, which, actually we have talked about that in chapter 2 already, right? The shape of the distribution has to do with bar graphs and histograms, right? And again, we covered that in chapter 2. Another thing that we want to consider is the center of the distribution. And measurements of center include mean, median, and mode, and that's what we're going to talk about in this section. And then we also want to be able to talk about the spread of the distribution, how spread out the data is. And the measurements that we use to discuss spread are standard deviation and interquartile range. We'll talk about standard deviation in 3.2. The interquartile range actually doesn't come up until later, I think 3.4, 3.4 or 3.5, I'm not exactly sure. But anyway, that's what we're going to be talking about in chapter 3. We'll talk about some other things in chapter 3 as well, measures of position and things like that. But the whole idea behind chapter 3 is, whereas in chapter 2 we were talking about visual summaries of data, chapter 3 now we're talking about numerical summaries of data. And consequently, this is where it's going to start to feel more like a math class, right? So up until this point, we've talked about a lot of like vocabulary definitions, and we've made a lot of pretty charts, or maybe not so pretty charts, but we haven't done a lot of like number crunching, and that's what we start to do now in chapter 3, is we start to actually crunch some numbers. So here's some notation that'll be useful for us just to help us get started. Whenever you see this symbol right here, this is the Greek letter sigma. It's a capital sigma, and it stands for sum, S-U-M. In other words, the sum is the answer to an addition problem, right? So when you see this big symbol in front of an expression, it means add up all of the values in the expression that follows, okay? That's what that symbol means. So it means add things up. And then in order to distinguish between the different observations within a set of data, we use subscripts to number them. So x1 represents the first value in the set, x2 represents the second value, and so forth. In general, xi would be the ith value in the data set. So putting those two symbols together, if you have this sum of the xi's, where I is allowed to range from 1 to n, then what that means is we're going to take turns plugging in numbers for I starting at 1 and stopping at n, okay? And then we're going to add those up. So if I plug in 1, I get x1. If I plug in 2, I get x2. If I plug in 3, I get x3, and so forth, all the way until I get to n, in which case I get xn, and then I'm going to add those expressions up, right? That's what this means. So let's walk through a couple examples working through some of these things together. It says, so here's our data set, 2, 2, 5, 6, 6, 7, 7, 8. Use this data set to calculate each of these things. So we'll start relatively easy with this one. This one wants us to add up all of the xi's, where I starts at 1 and ends at 8. So if I start by plugging in 1, I get x1. If I plug in 2, I get x2, x3, 4, 5, and I'm supposed to stop at 8. 6, 7, 8. Now, obviously, I can't just add those up. What would it mean to add like x1 plus x2 plus, I mean, you're not going to get a number out of that, but each of these stand for one of the values in the data set, right? x1 stands for the first value in the data set, x2 stands for the second one, x3 stands for the third one, and so forth, right? So really, this is saying 2 plus 2 plus 5 plus 6 plus 6 plus 7 plus 7 plus 8. right? That's 1, 2, 3, 4, 5, 6, 7, 8 values. Let's see what we get. So 43. Okay, so that's the answer to that first one. The second one is similar. It's just telling us to stop at a different place. This one wanted us to stop at x8. This one wants us to stop at x5, right? So this would be x1 plus x2 plus x3 plus x4 plus x5. So that would be 2 plus 2 plus 5 plus 6 plus 6. And then we would stop, right? Because that's 1, 2, 3, 4, 5. That's the first 5 values in the set. 2 plus 2 plus 5 plus 6 is 21. Okay, so this notation gets a little, I mean, it takes a little bit of getting used to right at first, but it's not terrible, I think. Let's look at this. More often than not, when we're dealing with this notation, we're going to be doing something something to the expressions, right? So in this case, what does this mean? This means, well, I'm going to do 3 minus x1. x1 is 2, right? So it's going to be 3 minus 2 squared plus, if I plug in 2, I get x2. It's going to be 3 minus x2. Well, again, that's a 2, right? Squared. Plus, then when I plug in I equals 3, I get x3. That's a 5, right? So this is going to be 3 minus 5 squared. And that's where I stop because I was supposed to stop at 3, right? So this means 3 minus 2 squared plus 3 minus 2 squared plus 3 minus 5 squared. And then you just simplify this using normal order of operations, right? So we do the stuff inside the parentheses first, and then we do the exponents, and then we'll add, right? So I'm going to have 1 squared plus 1 squared plus negative 2 squared. That's 1 plus 1 plus 4, right? Negative 2 squared is positive 4, right? Because negative 2 times negative 2 is positive 4. And that's 6, right? So that comes out to 6. Now compare and contrast that one with part D, right? It's almost the same thing, but notice that on part D, what you're squaring is the sum, right? Here you were squaring each entry and then adding them up. Here you're going to add up the entries and then square the result, right? So this one's going to look like 3 minus 2 plus 3 minus 2 plus 3 minus 5 squared. And if you're thinking, well, but isn't this the same thing as that? The answer is no. Exponents do not distribute across addition. So you can't just distribute this exponent to each one of these groups, right? It doesn't work that way. So what we would do is we would say, well, 3 minus 2 is 1, 3 minus 2 is 1, 3 minus 5 is negative 2. 1 plus 1 plus negative 2 is 0. And 0 squared is 0. So you can see that you do, in fact, get different results, okay? But that's that, right? That's how this notation is used. So far, we haven't done any actual statistics, right? I've just been introducing what this symbol means so that you know when you're looking at formulas, how to use the formulas, okay? Now, here's some statistics. In statistics, and this is not just in our textbook or just in our class. This is like anywhere in the entire world where some kind of statistical analysis is performed, a lowercase n always represents the number of data values in the sample. And an uppercase n always represents the number of data values in the population. Okay. Similarly, if you're talking about the mean, right? So the mean of a data set is the sum of all the values in a set divided by the number of values in a set. And the symbols that we use for that are universal, okay? Anytime you see an X with a little line over it, we read that X bar. And anywhere you see that in statistics, that stands for the sample mean, okay? This one down here, This is the Greek letter mu. Okay, it's the Greek letter mu. And anywhere you see the Greek letter mu, that stands for the population mean. Okay, and the way that we calculate them is the same, though, right? You add up you add up all the values and divide by the number of values. And add up all the values, divide by the number of values. Right? This is another way to say the same thing, right? You add up all the values, divide by the number of values. Okay. So going back to chapter 1, right? The sample mean, x bar, is a statistic, whereas the population mean, mu, is a parameter. Okay. Now, we make a distinction between the sample mean and the population mean because they could be different, right? Like, let's say that you're like measuring the height of a certain cotton plant or something, and we know from past experience that this particular strand of cotton, right, the cotton plants are 12 inches tall, okay? Like that's their average height. But you take a sample of cotton plants that have a sample mean height of 13 inches, right? So it's possible for your sample mean to be different from what the population mean is. And so we use different symbols to distinguish between sample mean and population mean, okay? So hopefully that makes sense to you, right? But yeah, we use different symbols. A lot of times we don't know what the population mean is, and we're using the sample mean to try to estimate it. So we say, well, if I got a sample mean of 13, then that means the population mean is probably somewhere between 12 and 14 inches, right? So if x bar equals 13, then mu is somewhere between 12 and 14, right? We'll talk more about doing those kinds of things later on in the semester. But that's why we like to have a different symbol for the sample mean versus the population mean. And this is a common thing in statistics. It's like we'll have one symbol for the sample statistic and a different symbol for its corresponding population parameter, okay? One last comment, when we go to compute these things, if you have to round, we usually round 1 decimal place further than the original data. So for example, in this next set of data, these are all whole numbers. So if we have to round the sample mean or the population mean, then we'll round to 1 decimal place. But if we were dealing with data that had 1 decimal place in it, then when we went to compute the mean, we would round to 2 decimal places, okay? So we round statistics 1 decimal place further than the original data. So let's look at an example. Okay, this one says, the following data represent the travel times in minutes to work for all 7 employees of a startup web development company. Compute the population mean of this data. Okay, well, since this is a population, the correct symbol to use would be mu. Right, so we're going to say mu equals. And then I want you to show me some work, right? If this were like a test or a quiz, I would want you to show me some work. You don't have to write down all of the numbers, but just show me that you know how to do the calculation. So for example, I might say something like mu equals 23 plus 36 plus ... plus 43. And that way I don't have to write down all the values, but I have shown my work, right? That would be sufficient evidence to me that you know what you're doing, okay? And then I'm going to divide by the number of values, 1, 2, 3, 4, 5, 6, 7. So you add up the values, divide by the number of values. So let's see what we get. 23 plus 36 plus 23 plus 18 plus 5 plus 26 plus 43 is 174. And 174 divided by 7 is approximately 24.9. Okay, so I rounded to 1 decimal place because that's 1 decimal place further than the original data, which was rounded to 0 decimal places. And notice that here I'm using an approximation sign instead of an equal sign. That's because 174 divided by 7 is not exactly equal to 24.9. It's approximately 24.9, but it's not equal to 24.9. So I don't say that so I don't say that this equals 24.9. I say it's approximately 24.9. All of these little details are things that I could mark you down for on tests and quizzes if you don't use them appropriately. So be disciplined and use them appropriately. If you're doing rounding, if you're doing any kind of rounding, then you need to use an approximation sign, not an equal sign. And again, on a test or a quiz, if I asked you this problem and you just wrote down 24.9, yeah, I'm probably going to mark you down some points for that. For one thing, I want to see you use the correct symbol. So if I ask you for the mean, I don't want you to just say 24.9. I want you to say mu equals 24.9, or mu is approximately 24.9, right? But then for another thing, like I said, I need to see that you know what you're doing. Okay, so you need to show me some work. Another reason to show me work, though, is for your own benefit. Because if you get the wrong answer, but the work that you showed was correct, I can still give you 4 out of 5 points, right? Whereas if you get the wrong answer and all you do is write down your wrong answer, well, that's 0 points. And what am I supposed to do with that when I'm grading it, right? I just give you 0 points on that problem. So show your work, right? Show your work. Okay, next one. It says the following is a sample of student test scores on a recent exam. Compute the sample mean. Okay, well, so this time it's a sample mean, so the appropriate symbol to use would be X bar, right? X bar in this case would equal 67.2 plus 84.3 and so forth, all the way until we get to 76.8, and then we're going to divide by 1, 2, 3, 4, 5, 6 this time. So let's see, 76.2 plus 84.3 plus 55 plus 61.2 plus 91.7 plus 76.8 is 436.2 divided by 6. And that comes out to exactly 72.7. So this time I'm not using an approximation sign because this wasn't an approximation. It's exactly 72.7 on the money. Okay, so so I use an equal sign instead of an approximation sign. Okay, and that's that. So that's how the sample mean works. Another measurement of center is the median. Okay, so the median is the middle value when the original data values are arranged in order. The symbol for the median is a capital M, and there is a separate symbol for the population median. The symbol for the population median is the Greek letter theta, but it's not very common. It doesn't come up all that often. So that's why it's not mentioned here. But to find the median, what you're going to do is arrange the numbers in increasing order. And then if the number of values is odd, then the median is the number located in the middle of the list. If the number of values is even, then the median is the mean of the 2 middle numbers. And I'll show you what I mean with an example. Okay. Okay, so I apologize. There's a train passing right by my house, and so it was making a lot of noise. So I just muted myself there for a second. But okay, but moving on now with this. So here's an example, right? So we have those travel times of the employees from the web development company on the first example on the previous page. And it says compute the median travel time of the employees. Okay, so the median travel time of the employees. Well, in order to do that, first we need to arrange this data in order. Okay, so so I'm going to arrange it in order from smallest to largest, 5, and then 18, whoops, and then a couple of 23s, and then a 26, and then a 36, and then a 43. Right, so there's the data arranged in order now. The median is going to be the number that's right in the middle. So in this case, 1, 2, 3, 4, 5, 6, 7. So the one right in the middle is this one right here, right? And you can verify that. I mean, you have 3 values to the left and 3 values to the right. So that one must be right in the middle. So the median is 23. Okay, and that's all there is. That's all there is to that. But now, part B says, suppose the company hires a new employee and her travel time is 40 minutes. Find the new median travel time. Okay. So now we've got the same employees as before, 18, 23, 23, 26, 36. But then we have this new employee whose travel time is 40, right? And 43. So this is what our travel times now look like. Well, if you try to find the value that's right in the middle, it would be right here, right? So that you're splitting it so that you have 4 values below and 4 values above. But what is that value, right? There's nothing there. So what we do is we take the average of these 2 that are closest to the middle, okay? So we're going to say the median in this case is 23 plus 26 divided by 2. 23 plus 26 divided by 2 is 24.5. Okay, so there's the median. Okay, so that's how the median works. So the mean is the average, right? You add up the values, divide by the number of values. The median is the number that's right in the middle when you arrange the data in order from smallest to largest. One last measure of center is the mode. The mode of a variable is the most frequent observation of the variable that occurs in the data set. If no observation occurs more than once, then we say that the data has no mode. Okay. On the other hand, you could have multiple observations that all occur the same number of times, and they all occur more frequently than the rest of the observations, in which case you could have multiple modes, right? So it's possible that a data set could have no mode, or it could have one mode, or it could have multiple modes. So here's an example. It says the web development company now has 8 employees whose commute times are these things, right? And it says compute the mode. Now, as far as I know, there isn't a symbol for the mode. So I'm just going to say the mode equals, in this case, it would have to be 23, right? That's the only value that repeats at all. So it would be 23. Now part B says the company's really expanding, so it hires 2 more employees whose commute times are 18 and 7 minutes. Compute the mode of the 10 travel times. Okay, so 2 more employees, right? Their commute times are 18 minutes and 7 minutes. And so now we're asked to compute the mode again. Well, so the mode in this case, we have 23 occurred twice, but now we also have 18 which occurred twice, and everything else has occurred only once. So since 23 and 18 both occurred twice, right, the mode would be both 23 and 18 in this problem. Okay? And then I'm going to add one last example. So let's say the company's expanding even more, so it hires 1 more employee whose commute time is 23 minutes. So another with commute of 23 minutes. Right, so they hire another employee with a commute time of 23 minutes. And now if we want to compute the mode again, now 23 has occurred 3 times, 18 has occurred twice, and everything else has only occurred once. So the mode is 23. Just 23. Okay, because it's the observation that occurred most frequently. Okay, so that's how the mode works. Okay, so again, the mean is add up the values, divide by the number of values. The median is the value that's right in the middle when you arrange the data in order. And the mode is the observation that occurs most frequently. Okay, so we have those three measures of center: mean, median, and mode. And the question is, why do we have three measures of center? Why isn't just one measure of center good enough, right? Or if we have three measures of center, then which one is the best? So I'm going to try to answer that question now, right? First of all, we like to use the mean whenever we can. The mean is the easiest to work with algebraically, and so we prefer it whenever we can use it. However, it's not always best to use the mean. The mean is not always a good indication. It's not always a good measurement of center, okay? And here's why. You know, for one thing, you can't compute the mean of qualitative data. For qualitative data, you have to use the mode, right? So to give you an example, here's that location of injury data again. This should look familiar to you because we've seen it in several sections now. Can you calculate the mean or the median of that data set? I mean, of course not, right? Of course not. What would it mean? Like, what would it mean to say back plus wrist plus elbow plus back divided by 30 or whatever it was? I mean, that you can't do it, right? So you can't compute the mean or the median. When you have qualitative data, the best you can do is to compute the mode. Now the question is, what is the mode? The mode in this case, well, let's see. It looks like back, right? It looks like back was the most common injury. We could look back in our notes to when we did this problem in 2.1. And yeah, back injuries occurred 12 times. So back was the most frequent observation. An important thing to point out here too is that the mode is not 12. The mode is back, okay? 12 is just the number of times that the mode occurred, but the mode itself is back, okay? So what is the mode? The mode is back. Okay, so if you have qualitative data, you use the mode, all right? If the data is quantitative, but not symmetric, then you would use the median instead of the mean. And that's because, excuse me, that's because the median is what we call a resistant numerical summary. And what that means is a numerical summary is resistant if very large or very small values relative to the rest of the data do not affect its value substantially. So, and I'll show you why the median is resistant, but the mean is not. But here's just a visual to help you understand, right? Our goal when we're measuring the center of a distribution is to figure out what is the typical data value. If you have a skewed left distribution, then these values out here to the left, even though there are only a few of them, they're so small relative to the rest of the data that it's going to skew your mean to the left, whereas the median is not going to be as affected. So the median is going to be a better measurement of the center of this distribution than the mean is. Same thing for when you have something that's skewed right, okay? The median is a better measurement of the center. So only when we have symmetric data do we use the mean, okay? So the median is a better measure of center than the mean when the data is skewed. To further explore this idea of resistance, I want to give you an example. So it says, below is a sample of salaries from a local diner. And let's compute the mean, median, and mode of these diner salaries. So, okay, so for the mean, right, the mean would be 85,000 plus 50,000 and so forth, all the way down to 30,000. And then we would divide by, well, how many people do we have in this sample? 4, 5, 6, 7 people. So we would divide by 7. So let's see what we get. Okay, so that comes out to exactly 45,000. Right, so the mean is 45,000. The median, well, that would be the value right in the middle when you arrange the values in order. In our case, these are already arranged in order, so we can see pretty clearly that Eric's salary of $40,000 is the median. And then the mode, that would be 30,000, right? That was the only observation that repeated. So there you go. There's the mean, median, and mode of this data set. So right off the bat, you can see that the mode is not a very good measurement of center when you have quantitative data like this, okay? Because 30,000 isn't anywhere near the center of this distribution, right? Most of the people in the sample made more than $30,000, okay? Whereas the mean and the median are both pretty good measurements of center, right? They're both pretty good indications of the center of this distribution. Now, Bill Gates walks into the diner, and Bill Gates, I don't think, has an annual salary anymore. I think he spends most of his time giving his money away, but I could be wrong about that. Anyway, but we'll just assume that his annual salary is $1 billion. So Bill Gates walks into the diner, his salary is $1 billion. Now watch what happens, okay? So if we go to compute the mean now, this is gonna be 1 million, right? Plus all of the other values divided by 8 this time, because now there are 8 individuals in the sample. Well, so if we calculate this now, it's gonna be 1 billion. Oh, I said million, but I should have said billion, huh? 1 billion. So that's 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 billion plus 85,000 plus 50,000. 45, 40, 35, 30, 30. Divide by 8, and you get 125,039,375. Okay, so there's the mean. The median. Well, we have 8 values now, so there's not a middle value. So the best we can do is take the average of the middle two, right? That would be those two right there. So the median is going to be 45,000 plus 40,000 divided by 2. And so the median is going to be 42,500. The mode is still 30,000. Okay. But what I want to really point out here is look at how much the mean increased. So before Bill Gates walked into the diner, the mean was 45,000 and the median was 40,000. After Bill Gates walked into the diner, the mean jumped to $125 million, whereas the median, it increased, but only a little bit. It increased from 40,000 to 42,500. So number 7 here says, for problem 6, which is a fair representation of the diner's salaries, mean or median? And the answer is clearly the median, right? Median. Because notice that nobody in the diner makes anywhere near $125 million. Most of the people make a lot less than that, and Bill Gates makes a lot more than that. Okay, so nobody makes anywhere near $125 million in this diner. Whereas a lot of people make pretty close to 42,500. So this is a much better indication of the typical diner salary. Okay, so for problem 6, which is a fair representation of the diner salaries? Median, because most people in the diner make about, or make close to $42,500 and nowhere near $125,039,375. Okay? So the median is a better measurement of center. And hopefully this demonstrates to you that the median is a resistant summary. When you throw in really large or really small values relative to the rest of the data, the median stays pretty firm, right? Whereas the mean, it's very, very badly affected by small and large values. So to summarize what we've said, which measure of center is the best? Well, if the data is qualitative, use the mode. Okay, if the data is qualitative, use the mode. Because you can't compute the mean or the median of qualitative data. If the data is quantitative, then you should use the mean or the median. You would use the mean if you have symmetric data. So that would be uniform or bell-shaped, right? So you use the mean if you have symmetric data, and then you use the median if you have skewed data, okay? And that's that, right? So that's it for measures of center.